So this, we are going to start a part which is new in the laboratory, in the physics laboratory. New in the sense that up to now you have not done it. This is the part of statistics, about which is the second part of the subject. And it is composed by these classes, which are a total of 9 sessions, which take place, all of them on Thursday morning. So that is all that is left from the year, 9 sessions. We'll have one of theory today, where I will speak a bit about descriptive statistics, which will be complemented by 2 sessions of computing work, where we will practice how to do some statistics work with Excel, okay? In the third year, you will do it with R, with different computing languages, and much more in detail. So this is only an introduction. And then we will have about 6 sessions of pure statistics, where our goal is to be able to explain this formula that we do at the beginning of the year, that we show in the first class, or that you saw in the first video, which explains how to estimate the random uncertainty from a number of measurements. Okay, this famous Tn minus 1 divided by square root of n, and so on. This is what we will see. So I hope to see all this part before Easter, and the second part will be after Easter. This is the bibliography you can use for this part. And as you saw, we only have 9 sessions, and this book have about 400 pages. So they are much more than enough. But still, some of them are easy to read. For example, this one, which is in Spanish, or this one is easy to read. It's very, very thick, but thick as a brick, they say. But it has many, many examples, and it's very easy to follow. Okay, and this one is available online and has many, many examples also. So what is statistics? What we are going to see, and it is the branch of science that is responsible for collecting, analyzing, and interpreting the data. So this is purely experimental work, although you'll find that it has some applications to quantum mechanics and to statistical physics also. So what we will say will be useful for you in these subjects. Not the part we're going to explain today, which is about descriptive statistics, which is only responsible to collect the data and to describe a set of data in terms of a few parameters, which are parameters related to localization and variability of your set of data. So this is the class is divided in 2 parts. And this is the syllabus for the first part. Okay, first we see what are statistical variables, then we'll speak about frequency distributions and how to build frequency tables, both for ungroup data, and then we'll say 2 words about graphic representation. I think many of you may have seen this already in high school, but others have not. So I am forced to do this to try to level up the curve. Okay, so concerning the statistical variables, there are 3 concepts that you must have in mind. First of all is population, second one is sample, and third one is characters. These are the 3 main concepts related to statistical variables. The population is what we want to study, the complete set of elements we want to study. For example, when they make a poll to try to infer the result of an election, the population would be the whole population of Spain who can vote. This population can be finite, for example, the population of Spain, or can be infinite or very big, like the number of stars, or the number of outcomes from an experiment, which will be the thing that will interest us most. But we cannot measure all these 40 million, we cannot ask all these 40 million persons, whatever. So what we do is to choose a sample. A sample is a subset of the population elements that we use, that we study, we measure in detail, and we use to infer things about the population. For example, a sample is the 5 measurements you take in the lab. That is a sample of a large population. And then on this sample, we study something, which are the characters, which may be quantitative or qualitative, depending. For example, we may study the period of the pendulum. We may study the resistance of a circuit or whatever. Okay. And then our statistical variable is this data we're studying, the same thing basically as the character we are studying. So the statistical variable is the character we are studying, and it can be, if it is quantitative, let's put aside the cases where we are studying things like which kind of music do you like, or like what do you prefer, dogs and cats, and center in numbers. And then, although this can be studied also with the statistics, but then if we only take quantitative characters, then they can be discrete or continuous mainly. So discrete 1 to 3, and they map on the natural numbers, and continuous when they map into the real numbers. Okay, either R1 or Rn. They can be one-dimensional variable or n-dimensional variables. We'll study in this course only one-dimensional variables, so things that map into R1. And remember that in practice, all measures are discrete, even if the variable is continuous, because the devices do not allow for infinite possibilities. So finally, what we see in discrete variable we will be able to extrapolate to the continuous variable. So let's start with an example. Let's jump onto frequency distributions. You will need a piece of paper, okay, because we're going to do just very simple numbers, so to make it easier to fix the ideas. And let's start with this example where the government wants to find out whether the average number of children per family has fallen from the previous decade. Okay, and for this, it surveys 50 families, and it asks the family about the number of children they have. And this is what the families are answering. One of the families, sorry, one of the family, two children, another four, another two, etc. Okay. Then, can we identify in this example what do we just define? Well, yes, it's easy. The population will be the set of all families in the countries. That is what we want to study. The sample is our 50 families we have surveyed. The variable is discrete, and it's the number of children. And the variable type is discrete, okay. So what is the first thing we do to study? We want to reduce, we have, for this example, 50 numbers, we could have 50,000. So first of all, we want to systematize this and to reduce the number of data. So for this, we build a frequency table. That is the first thing to do. This is what Excel will do for us, as we will see in the next classes. A frequency table is a table like this, where you have in the first row the values of the statistical variables, ordered normally from the smallest one up to the highest one, then absolute frequencies, relative frequencies, cumulative absolute frequencies, and cumulative relative frequencies. I'm going to explain it in the next slide, the meaning of this. So absolute frequencies is simply the number of times that a value appears. How many times does a value appear in this table? Okay, how many times do we have a 3? How many times do we have a 2? Relative frequency is the absolute frequency divided by the total number of data. So it's like the percentage, but related to 1. Okay, could also be expressed as a percentage. The cumulative absolute frequency is the absolute frequency, but includes also all data which are equal or smaller than a given one. Okay, so we'll see this as an example. So it's the sum of all frequencies that correspond to values that are equal or smaller than the one we are studying. And the cumulative relative frequency is the same thing, but for the relative frequency. So if we go to our table, first of all, we sort our data. We start with 0, and we go up to the highest number, 6. And now we are going to build the frequency table. Okay, so I have already sketched the table here, and your task now is just to complete it, just to fix the concepts. Okay, so I have drawn the table and I have counted the numbers. So here I have the absolute frequencies. I have counted that there are 2 families with no children, 4 families with 1 child, 21 families with 2 children, and so on and so forth. If I did it correctly, and this is a check, you have to do the total number should be 50 because the survey was taken over 50%. So take that just to fix what is the meaning of the. I don't want to be too slow. I have time, but I want to do the example sample. So fill the missing data in the table. Let me check meanwhile. Is Alejandro Carrasco here?
Yes.
Ah, okay. Just wanted to know if you had joined the call because you don't see well the black the. Yeah. Okay. Good. Good. No problem. Just wanted to know. Okay. Do you have the table, or if not the whole table, at least part of it? I'll wait a couple of minutes more. Yeah.
I don't understand what the concept cumulative absolute frequency and cumulative relative frequency.
You will see it very easily when I show the numbers, but basically it's just take this number. For example, take this frequency and all those that correspond to a smaller value. So for 0, it will be 2. For 4, it will be 4 plus 2. For 2 will be 21 plus 4 plus 2, and so on. So it's how many values you can find that are, how many families you can find that have 2 children or less. That's the cumulative absolute frequency.
And it will be 2 children or less, 4 children or less.
Yes, that is. It's the number, the frequency for 2 children or less.
And all divided into the n.
This is the absolute cumulative, and the relative cumulative is divided by 50, by the total number. So it would be something like the probability of having 2 children or less. But okay, you can just present it. Okay, so let me show, even if you have not completed it fully. Let me show you. At least you must have numbers similar to those. Okay, this will be the full table. So this is the cumulative absolute frequency, as Juan just asked. This is the relative frequency, and this is the cumulative relative frequency. You can compute the cumulative relative either summing up the relatives or from the cumulative or normalizing the cumulative one, of course. Either way works. And what is important is that this table summarizes everything we know about the sample with no loss of information. Well, in fact, it has more information because it's easier to understand. And this part already summarizes everything we know without losing any information. These two vectors, they have the same information as this whole of 50 numbers. And the same thing would apply if we had 50,000 numbers. Okay, so that's the power of statistics. Okay, let's go on. How do we represent this? The standard way to represent discrete distributions, well, data for discrete variables, is a bar chart. It's simply to draw bars where the height of the bar is either the absolute frequency or the relative frequency or whatever you want, one of the frequencies. You have to specify which one is it, of course. And you should leave gaps between the bars to show that you are not giving the relative frequency for 1.5 children, which has no sense. So there should be holes between the bars. This is not needed to put the numbers on top, but this is a simple graphic representation which is easy to use. Okay, so let's go on to the next example, and it's an example where we are going to use class intervals, which is applicable to continuous variables or to variables which have so many possibilities that making the whole table is not an option. Okay, here it was very easy because we only had 6 possibilities, 6 values. Imagine we have 600, we cannot draw this table. So what do? We group the possible values of the variables in classes, and these classes are defined by a lower limit, a sub I, and an upper limit, a sub I plus 1. So the class will be defined by A1 to A2, A2 to A3, etc. And these classes are represented by a value, which is normally the middle point of the class, of the interval. You will see it very clear with the next example. And this value represents all this set of values. So we're going to lose some information here. The rest is exactly the same: absolute frequencies, relative frequencies, cumulative, and cumulative. So let's go for another example. And imagine that a new hotel is going to open the doors in a certain city. And before, in order to have an orientation of the price they have to charge for the rooms, the manager goes around, looks at 40 hotels in the neighborhood, and gets these prices where the prices are in tens of euros. It's a cheap city. So 39 euros, 47 euros per night and room, okay, and so on. So just for a moment, let's check what would be the concepts in this case. The population is all the hotels in the city or in the neighborhood, more precisely in the neighborhood. The variable is the price of a room for one night. This variable in principle is continuous because they can charge whatever they want, 47.2321. Makes sense? Although in practice, we have rounded it and we only have some values. And since there are many different values, you see there are many different, we will use intervals. So how do we do this? First of all, we have to define what is the range. The range is the highest value minus the lowest value. Okay, we have to know that prices of room go from some value for 33, I think more or less, to 61 euros per night. This is the total range of values. The interval in the real line where the data are found. Then we have to choose the number of intervals, how many intervals we will use. If they don't tell us anything, then we will choose something like the square root of the number of data. It doesn't have to be exactly the square root, but something close to the square root of the number of data, because in that case, you will have as many intervals as data in each interval. Okay, you understand? If you choose the square root of the number of data, you will see in this case. Then we have to choose the class width, so the width of each interval, the boundaries, and the class mark. I prefer to explain it with the example. So let's go on with this example. First of all, the range, the number of classes, the class width, the boundaries, and what is the range? The range is the largest value minus the smallest one. So 61 minus 33 is 28 euros. That is the range. Number of intervals. We have 40 elements. The square root of 40 is 6.3. So we'll choose 3. We could have chosen 7 also or whatever. The class width. Now, all this is approximate and depends on the study. As the range is 2.8, if we divide 2.8 by the number of classes, which is 6, then we find a class width which is 0.46. But this is difficult to remember, better round it to 0.5. Okay, so we will choose a class width of 0.5, which means 5 euros. Okay, in our units. The boundaries of the intervals. We have to define these numbers here. The first class goes from this value to this value. We're going to choose them in such a way that it's very easy to see if an element belongs to one class or to another class. And the easiest thing is to choose boundaries that have one more decimal than the values you have in the table. So for example, the lowest boundary, we have that the lowest value is 3.3. So the lowest boundary will be 3.25. So 3.3 will be larger, and if we have 3.2, will be lower. There's no way to make a confusion. Okay. So what will be the highest value? We have 6 intervals. The width is 0.5, so the highest boundary will be 6.25. So finally, this is our table. It is a generalization of what we had before. And here you have, it's a pity, I should have used points for the decimal sign, because otherwise they get confused with this comma. The first interval is the rooms, which are between 32.5 euros and 37.5 euros, or 33 point. Second interval, third interval, and the most expensive rooms are those going from 57.5 euros to 62.5 euros. Okay, now we have that table. How do we represent these classes? Just by the middle point. Okay, so if we take the average of 3.25 and 3.75 is 3.50. And we will say that all these rooms have the price around 35 euros. So we are losing information because, for example, we know that they are cheaper than 25, than 35. Okay. So the idea would be to complete the table and do exactly the same thing as before. Just try to count there, if you can feel it, because the rest is exactly the same. Okay. So the idea is only compute the absolute frequencies. Absolute frequencies is how many rooms you have in this range. And there I have used this sign to represent the open interval and this one to represent the closed interval, but it doesn't really matter because there is no value which falls into the boundaries by definition. Okay. The way I have defined it with one more decimal place, it's impossible to have a value of the boundaries. Okay, it's just counting, but I think it helps to fix the ideas. Okay, are you done just counting? I guess quite a lot. So let's see if you get these numbers, more or less. So in the second class, we have 8 rooms. In the third class, we have 14 rooms. In the fourth, 6 rooms, 4 rooms, and 5 rooms in the following ones. And if we did it correctly, then the total sum should be 40. If you sum the relative frequencies, which I did not, you would get 1, of course, because it's the person. And the last cumulative absolute frequency should be equal to the number of data, 40. And the last cumulative relative frequency would be 1, because it's just the proportion of rooms which have a price equal or lower than the most expensive one. So all of them, okay, all of them have a price which is equal or lower to the most expensive one. So this is our table. It summarizes everything that the manager needs to know to build his hotel. And if his hotel is normal, it will make sense to have a price around 45 euros per room in the average. Okay, that is what he can extract from the table. But remember that here we are losing information, as I told you, because we are grouping all these 3 rooms in the same class, and we are giving them the same absolute price, although they have not. So we lose a bit. The more intervals we build, the less we lose. How do we represent it? In a very similar way as before, with a bar chart, but this time we join the bars. By the side, the bars cover the whole range. Remember, the range was going from 33 to 61. So, sorry, to 3.3, from 3.3 to 6.1. We join them to say that any value in between is possible, to show that any value between them is possible. No need to put the numbers, but I put them just as a reminder. We specify the units. Units are frequencies. Frequency don't have units of physical quantities, not hertz. Okay, it is a frequency in statistical terms. And normally each of these channels is called a bin. This is jargon of histograms. It's called a bin of the histogram. Okay, each one, each of those. Good. So instead of using this, we could use different representation. You have many of them. This is the one we already saw. This is the one we also saw for continuous variables. Okay, just read what is it. This is sometimes called the frequency polygon, where you join the points with a line like this, instead of making bars. When you have cumulative frequencies, if they should always touch each other. Okay, and because it's always the probability of something lower than, and they should always grow. If the variable is ordered, they should always grow. And you can also use pie charts for the relative frequencies, not for the cumulative frequencies, would not make sense. But you are used to pie charts where the angle is proportional to the relative frequency of the class. Okay, something like that. Good. So this is the first part. You have a lot of data, how you group it, and how you summarize it in a histogram or in a table. Okay, now we're going to go further, and all this data we're going to summarize it by a few numbers, a couple of numbers, by the average and the standard deviation, more or less. And this is what we are going to study. What are the different ways to summarize this data? Okay, there is a story for people who like Indian philosophy that there was a guy who wrote 6 books, the Vedas, where he wrote all the wisdom that there was in India. A very wise man and collected, and he wrote these books. And there, a wiser man came down and he summarized everything in just one book. And then an even wiser man came down and he summarized all the information in 2 words. Okay, so this is what we are going to do. First, we collect the tables, we write the 6 book, then we summarize it, and finally we summarize it in 2 words: the mean and the standard deviation, more or less. Okay, this is what we are going to do. So first of all, we'll study measures of location. Imagine that this is like a mountain. We have our histogram, our bar chart, and you can imagine the bar chart as if it was your bar chart, which is something like this. You can imagine it is a mountain. So first of all, we are going to give measures of location. Where is the mountain? More or less where the highest peak is, where the average peak is, where is it? And then measures of variability. How large is the mountain? Okay, basically, this is what we are going to say. And finally, we are going to say a word about what is the relation between both, between the size, how high is the mountain, and how wide is it. So let's go on. First step, this is what I just said. How are we going to locate the mountain? What is the location of the center of the data? We are going to study these 3 quantities. Well, these 4 quantities. First of all, the mean, the median, the mode, and the quartiles, deciles, and percentiles. These are the 4 ways we will use. And then to study variability, we'll see the range, the variance, and the standard deviation. And perhaps say a word about symmetry measures. So the easiest one you have always seen is the mean. You take all the data, you sum it, and you divide by the number of data. This is a way of saying where is the center of the mountain. For example, if for some reason you miss classes during the week, and this is the number of classes you did miss each day, you compute the mean, and each week you miss around 2.2 classes. Okay? And you leave it like that. You don't round it. The mean can be more precise than any of the number. It has to be more precise than any of the number. Okay? So never mind if you have numbers with no decimal places, and by doing the mean, you get one more decimal place. It's normal, or even 2. Okay? So when you are in the lab. What is the problem of the mean? The problem is that it is very affected by what is called in a statistic outliers. Outliers mean that lies out. So, for example, imagine that you are ill, 1 week you are sick, and you miss 12 classes. Then you would get a very high mean, and that is not the reality. Imagine that you have this mountain, and you have a small elevation up there. Okay? Then you compute the mean using this formula, and you find that the mountain is there. So it is almost true, but it's not exactly what we mean by the concept where is the mountain. Okay? This is what they say in statistics often also, that you have heard this, lies, dumb lies, and statistical lies. No, you must heard it. As you progress into things which are worse. For example, if you eat, they always give the same example. If you eat a chicken and I don't eat anything, each of us has eaten half a chicken. Okay, so the mean is not representative of the reality in this sense, because very large differences give to things which are not representative. That it is a problem, and when you analyze your data in the lab, you should take care to eliminate these things which are probably experimental errors. So how do we compute the mean? If we have made our tables, we could compute the mean from the tables, multiplying each of the values times the absolute frequency and divided by total number of data. So if we operate this, the mean would be the values multiplied by the relative frequencies. That is the way we can compute the mean using already the table information, not all the results. And if the data was grouped in classes, then we would use the marks of the class, and we would do exactly the same. So the mean would be the sum of the marked classes multiplied by the relative frequencies. Okay. For example, if we have our rooms, we can do it in two ways. Okay, this is the data for the number of children. We can either sum all the values and multiply by the frequency, each value multiplied by the frequency, sum it all and divide by 50, or multiply each value by the relative frequency, and we would get 2.52 in any case. If we go to the example of the rooms, we could do the same thing. Either get all the rooms individually, compute the sum, and we would get 46.7, and we could use the group values, and we would get 46.8. These are a bit different, you see, because we did lose some information when we group the data. This is the result for them. Okay? Just remember that it's easy to use this formula to compute the mean from the group data, from the table. What are the properties of the mean? Well, first of all, if you sum the deviations of all values with respect to the mean, you get 0. This is just showing that the mean is somehow in the center. So if you sum all the deviation, you get nothing. So it will have some implication in what we do later. This is the proof of it. The second property is what we said, that it is not very robust. The fact that it is very affected by outliers, those points there, is said in statistics that it is not robust to small changes. If we multiply the data, if we do a linear transformation of the data, multiply the data by some number and add some number, this would be a linear transformation. What happens to the mean? Well, the mean gets multiplied by the same number, and the same number is added to the mean. This is a way to, if we have a mean which is not 0, to take the mean to 0, to center things, to center distribution. Okay. Second way to measure the localization of the mountain, the median. The median is normally called ME, and it is the central value of a series of value. You order the data and you find the value such that 50% of the data are lower and 50 are higher. So you come here and you say, you get this number, you sum this number until you get to 50%. Imagine it is here. Then this will be the median. And since we are counting values, this one over there doesn't matter so much. It doesn't matter at all, nearly. It's only one value, okay? So a strange value, the median is very robust with respect to this. And what would happen if instead of finding it's in the middle of a class, no problem. It can be in the middle of a class. We just count how many elements we have in this class, and we separate it such that we have n elements and n elements, assuming that they are equally distributed inside this bin. Okay? Assuming that the elements are equally spaced inside the bin. This is what we would do to compute the median. It's also called percentile 50. The median is also called percentile 50 in the sense that 50% of the values are smaller than the median by definition. That's the way we define it. Good. Third way we use the mode. Mode is in Spanish like fashion, so it's the value that appears more often. So we define the mountain by the highest peak, by this one. Okay, this is another way, and then we would have the mode there. It would be relatively robust also. And the problem it has is that maybe there is not a single mode. We may have several. We might have two peaks which have the same height. And in this case, we would have to give both values for the mode. So we would say that this distribution or this data is bimodal. It has two modes. Okay. No problem. It's already giving information about the data. Good. So this slide tries to give an idea of how these values can be different for a histogram, for a set of values we have measured, classified. Look at the first one. In the first one, we have, if you think a bit about it, the distribution is asymmetric to the right, okay? Then the mean will be pulled by these values to this side, and the mean will be greater than the median. And if you look at the mode has to be this value, which is the highest one. So it will be also, the median will be greater than the mode. Okay, is it clear? Yes?
I don't understand really well why the mean now is higher. So there are more, let's say, little small values that are bigger.
There are, yes, that is the trick. Exactly, it is higher because of that, because there are more small values than higher. So they weigh less, in principle, they weigh less. And these values here, which are farther away, they pull the mean away from them. The thing is that the few large values are farther away. So when you do the mean, you multiply each value by the distance, and this is pulling the values to the right. This should be like that. I don't have specific values, but intuitively it should be like that. And the fact that there are more small values makes that the mean is greater than the median. The third thing is just by construction, because I did put the highest peak there. But the difference between mean and median is just what you said, due to that. This is a perfectly symmetric distribution, and in that case, everything is the same. The mean will be equal to the median, will be equal to the mode. And this third distribution is skewed to the left, to small values. We have more high values than a small one, and in this case, the mean is pulled to the other direction. Okay. So this is the difference between the three values. Next concept, these are the main ways to specify the location of a set of values of distribution. But there are some auxiliary ways, which are the quartiles, deciles, and percentiles, which are generalizations of the concept of the median. Quartiles are values that divide the sample in 4 equal parts with 25% of the data. So you go there, and you find which are the 4 values. One here, for example, quartile 1, one there, quartile 2, quartile 3, and quartile 4 will be, well, I think I didn't do it correctly, totally correctly, but this is the idea. The idea is that you have 25% of the values there, 25% of the values there, 25% there, and 25 there. Okay, so you split the sample in 4 parts. And the same thing, well, you have a short example there. The same thing will apply if you split the sample in 10 parts or in 100 parts. These are just the boundaries that define how you do the splitting. Yes?
Could it be that because one of the beans is so large in comparison to others, that two quartiles coincide, that are the same?
In the case you have this, what you're going to do is, as we said before, you're going to assume that inside these large beans, values are equally spaced, and yes, they could coincide. Well, you're going to assume that values are equally spaced. So if this bean is large enough, they will not coincide, because you will assume, for example, imagine we only have one bean, extreme case, only one. Everything is in one place. Okay, imagine we only have one bean, like this. Then you would draw them 1/4, 1/4, 1/4, 1/4, because you will say that all of them are equally distributed. Okay. I always draw this example, it's partially in Spanish, sorry, because I took it from the ministry data. This is an example of where to use the deciles and the percentiles. Well, the percentiles I will explain later. This is the weight earners by sex and decile during the year 2011. This is an example of how to use the deciles to characterize a population. So what does this mean? This means that the part of the population, the 10% of the population that earns the lowest wages in Spain, that was earning the lowest wages in Spain in 2011, was composed, well, was earning less than 687 euros per month. So that this value here, our first decile, was 687 euros. Okay. This is in general for the population. If now you split it into women and men and women, sorry, then you find that this is 4.4% for men and 60.3% for women. So I mean, if you count persons who earn less than 680.1 euros per month, you find that 4.4% of men and 16.3% of women earn that amount. Okay, this is what they usually call the gender gap. This is the way to specify the gender gap. It does have no political implication for me. I mean, this is just data. It could be, and I think it is in many cases, that women take part-time jobs quite more often than men, which is a problem, right? But okay, this is the way to express the data. Okay, if you go up, you will see that, for example, the last decile, the one which is there at the end, is composed of people that were earning more than 300 euros, more or less, per month. So 10% of the Spanish population at that time, 10 years ago, was earning more than 300 3,300 euros per month, and this is the composition into men and women. This is data that the interesting point for me about this is that this is data that summarizes very well what is happening, and this is provided by the ministry each year. This is called the Encuesta a la Población Activa, I think, and it's provided by the Ministry of Economy each year. And if we look, I think it helps to see what is a decile. It also helps when you have a baby and they say your baby is percentile 50. It means your baby is perfect, it's in the middle, it's heavier than 50% of the babies and lighter than 50% of the babies. If your baby is percentile 99, it means it's fat. No, it's very fat. By the way, it doesn't matter at all. No, it doesn't matter at all because it happened to me and everything went perfect. But this is the first time normally people find percentiles is with baby, and then you find babies. You find out or parents say, my baby is 83, my baby is 22. Okay, but it's a way of visualizing. By the way, this is what happened in 2017, a bit later. And as you see, first of all, things were leveling a bit between men and women, a bit at least. Unfortunately, the highest salary was growing. That means that the Spanish economy was growing a bit. Okay. So that is the data. Good. So let's go to measures of variability. Up to now, we wanted to know where is the mountain, and not only where is the mountain, where is the first 20% of the mountain, where is the second 20% of the mountain, and so on and so forth. Now we want to know how wide is it. And we are going to study 3 measurements of variability: ranges, median deviation, mean deviation, and variance and standard deviation. So first of all, ranges. A range is the difference between the highest and lowest value. So if we have our mountain here, let me draw it again and erase all this. Let's leave this stone there. Okay. It will be useful for us. This mountain is our histogram. So the range would be from this value to this value. Okay, this would be the range of our value, from the smallest one to the highest one. So it is also affected by outliers. Okay. Maybe it's better to look only at the interquartile range. Interquartile range is from quartile 1, Q1, Q1, to quartile 3, Q3. It will be this part, and this is basically what is the central part of the population. What is the central part of your data? So if the data is evenly distributed, the interquartile range would be half of the total range. Okay, if everything is flat. If things are not flat, then you can measure from that. And then the semi-interquartile range, which is half of it. But okay, this is not easy to compute because you have to compute a lot of frequencies. Would it be easier to compute this? That is the mean deviation, the deviation with respect to the arithmetic mean. You compute the deviation of each value with respect to the mean, and then you average. What is the problem if you do this? If you compute the deviations with respect to the mean and you average them, that you get 0. You remember that from the previous value that the mean was in the middle. So you get 0. It's impossible to do that. So what you do is to compute the absolute values of the differences and to weight them by the frequencies. This could be, but this is seldom used. This could be a good measurement of how wide is your set of data, but this is seldom used because the absolute value has awkward mathematical properties. It's difficult to work with. Okay, so normally this is not done. It could be a measurement of variability, but it's seldom used. What is done instead is to do this. That is what we'll do all the time. That is to compute the difference with the mean, square it, and average it. Okay, and then we divide also by n minus 1. We will see later on why it's better to divide by n minus 1. It is basically, the basic idea is, which you will see in the next slide, is because we are computing it with respect to the mean. And the mean is a privileged point in the sense that the mean makes this smaller. Okay, so using the mean makes this measure of variability artificially smaller than it should be. And that's why we divide by n minus 1 to make it a bit larger. So we have the mean, we compute the distance from the mean to its value, we square it, we sum all of them, and divide by n minus 1. Since we have squared them, at the end we'll have to, this is the variance, and then since we have squared them, if we want to know the deviation, then we take the square root at the end. So this is the standard deviation, and this is the variance. These are the ways the most used ways. What is the problem? First of all, it is not a robust measurement either. Why? Because that stone over there, now it's much worse. Because the distance from the mean will be here to this point will be a square. And the square will make this, squaring it will make the weight of this point much bigger. So if you have a wrong point, a point which shouldn't be your sample, a point where you have an error, and you compute the standard deviation, you're going to screw up on your measurements. Okay? You're going to spoil all your measurements just because of this point. So it's better to look for bad measurements and take them out. This is what is said in this case. So what do you have to do? You want to have a robust measurement, then do your work and go to the interquartile range. Use something like that. Okay. And this is important to remember. I remember I was in the jury of a thesis 2 months ago, and the guy was doing that, and he was obtaining negative values for a thing which should not be that. Yes.
What is the problem?
Well, the value divided by n. We'll see later in the statistics, but I mean, intuitively, the thing is what we want to get is an idea of what is the spread between the. And if we go to the next slide, I think it is there. You can show that if you want to compute these square deviations with respect to any value a, then you would find that the minimum is when a is equal to the mean. Okay, so somehow your result is biased because you have computed it with the point using the value which makes it smaller. So you are getting an estimation which is somehow biased towards smaller values. More or less, the intuitive idea is clear. Yes?
Because the mean is smaller than most of the value.
Not the mean. The result of the variance or the result of the standard deviation when you compute the result of the square, the mean of the square, when you compute it with respect to the mean. Not that the mean is smaller, it's that the result of this square average. This is an average, but I don't know if I am answering your question. This is an average of all the square distances from the values we have to a given point, either divided by n minus 1 or divided by n, I don't mind. But this average will be smaller when you compute it with respect to the mean. So the mean is so special that you are obtaining two small values. For example, in particular, imagine that there is a true mean, there is a true value, okay? But you're computing it, your result not with respect to the true value, but to the value to the mean you have computed with your data. Then your estimation will be smaller than the true one. Okay, that is the main point. The main point is that if you were to compute it with respect to the true value, then you would get a larger value. Because you have computed it with the mean of your data. That is the bias. With the mean of the data you have measured. So it's somehow you you are tricking a bit, you are cheating a bit. Okay, this is correcting. It can be shown that subtracting one corrects most of the cheating. Okay, just 5 minutes. What happens with the standard deviation when we do a linear transformation? Well, it just multiplies by the factor you multiply the data, and it is not sensitive to displacement. Okay, and then okay, we have defined the mean and this standard deviation, and it looks just like a way to estimate the width. Okay, the width of our so-called mountain, very well, but it has some surprising mathematical properties. Imagine you have this table of 20 data, you compute the mean, you compute the standard deviation, you find 0.0010, and then you count how many points are between the mean and then plus the standard deviation and the mean minus the standard deviation. So you make an interval, you build an interval, center on the mean, you center the interval on the mean like we do with our uncertainties, and this interval goes to the mean up to the mean plus the standard deviation and the mean minus the standard deviation. Okay, then you take this data, you count, and you find that 80% of the data is there. So, okay, I was lucky because the mountain could have very different shapes. And then you make the interval a bit larger, minus twice the standard deviation and plus twice the standard deviation, and you find in this table that you have 90% of the data. It's very close to this 95% confidence level that we use in the lab. So is this due to luck? Is this because I was preparing the data to have this? No. The answer is no. The answer is that there is something which is called Chebyshev inequality, which tells you that if you do this for any set of data, that for any set of data you compute the mean and the standard deviation, doesn't matter how is it, then you will find that the probability to have the number of points, or the probability that you have inside this kind of intervals built with the mean in the center and n times the standard deviation is given by 1 minus 1 divided by k squared, where k is this number. So in our case, you should always have at least, well, it doesn't tell you anything for the plus 1 minus 1, so this was chance. But for the plus 2 minus 2, it tells you that you should have 75% of your data there. And for the 3 times the standard deviation, you should have close to 90% of your data. So this means that the standard deviation is really a powerful way to estimate the width of your data. Yes. Okay. The 3 times the standard deviation should be percentile. This point there with 3 should be percentile 89. Okay, that is what the theorem is saying. It's understood that this part is the beautiful. And then finally, we define the Pearson variation coefficient that gives a measure of the variability of the data as the result of dividing both numbers, the standard deviation and the mean. And sometimes we express it as a percentage. Realize that they both have units and they have the same units. Standard deviation and mean, they have the same units. So this coefficient will have no units. It will be okay. This is all I wanted to tell you. Do you have any questions? Yes? Okay. So read the slides, it's quite simple, and then the next 2 sessions will be in the computing room and we will use Excel to compute this kind of measurements for sets of data. Okay.